of the ordinary Big Bang theory without inflation. Inflation will change this aspect of it. But for the Big Bang theory without inflation, the only way you could explain that really was to assume that the Big Bang was uniform to start with, filling space, not happening at some particular location. The Big Bang theory is very successful. It explains how the early universe expanded and cooled. And the actual mathematics of that, by the way, is very simple if you ever want to look at it in detail. It's not complicated at all. It also explains how the late chemical elements formed. The Big Bang theory starts to describe the universe when it was so hot that even the nuclei of atoms would not have been stable. So the atoms have to be made later as the universe cools. And the study of this began in the 1940s with the work of George Gamow and his collaborators. And they gave up in frustration because they couldn't figure out how to make any elements heavier than lithium in any significant quantity. We're now believing that they were entirely right in their calculations, not in complete detail, but the conclusions were right, and that elements heavier than lithium were in fact not produced primarily in the Big Bang. Elements heavier than lithium were produced, we now think, in the interior of stars. And then when stars explode, they spew these heavier elements out into space, ready to recollect into a later generation star. And our sun would be one of those later generation stars. So essentially all of the stuff that we're made of would be material that was synthesized in an earlier star and strewn out into space and recollected to eventually form ourselves. But there are still 4 or 5 lightest isotopes, which we do think were produced primarily in the Big Bang. And the Big Bang theory can be used to calculate the expected abundances of those different kinds of isotopes. And those calculations work very well and are one of the strongest pieces of evidence that we have that the Big Bang theory is correct. And they allow us to trace the Big Bang theory all the way back to about 1 second after the actual instant of the Big Bang. That's when the processes that produce the light chemical elements were just beginning. Finally, the standard Big Bang theory describes how matter congealed to form stars, galaxies, clusters of galaxies, and so on. That's certainly still a work in progress. We don't claim to absolutely completely understand how galaxies form. But everything we believe is consistent with the idea that these things form simply by the gravitational attraction of matter for matter, which causes matter to coagulate. So these are the successes of the conventional Big Bang theory. But since I want to talk about modifying it, I want to talk a little bit more about what the conventional Big Bang theory does not describe. Now, there's nothing about the conventional Big Bang theory that we actually think is wrong. It does work and gives a good description, as far as we could tell, of the universe around us. But there are a number of questions, nonetheless, which the classic form of the Big Bang theory simply doesn't address. And inflation fills the gap of providing a way of addressing those questions. So they basically all hinge about the fact that the classic form of the Big Bang theory was sort of haphazardly named the Big Bang theory. It was actually named by people who thought the theory was ridiculous, and they were trying to think of the most ridiculous name they can come up with, and they called it the Big Bang theory, and it stuck. But the key point is that the theory is not really a theory of the Bang at all. The scientific version of the Big Bang theory says nothing whatever about the Bang, but really is just the theory of the aftermath of a Bang. It starts after the Bang has taken place. It assumes from the beginning that we had matter spewing out with all the matter moving away from all the other matter in a neat pattern. But the forces that cause that motion are not included at all in the theory. The other important shortcoming of the conventional Big Bang theory is that it doesn't say anything at all about where all this matter came from. Now, you may be surprised to hear that it's even possible to talk about where the matter of the universe came from, but in fact, I will try to convince you that this inflationary theory really can explain where almost all of the matter of the universe came from. It doesn't quite get it all, so there's still room for further work on the subject of how the universe actually originated. So what is inflation? Inflation is a modification, as I've already said, of this conventional or standard Big Bang model. And the kind of modification it is, I think, is best described by a word that was probably invented in Hollywood. It's a prequel to the Big Bang theory as we know it. That is, it describes the events that preceded the events that are described in the conventional Big Bang theory. And in particular, inflation can explain the bang of the Big Bang, by which I mean the forces that drove the universe into this tremendous propulsion, tremendous expansion that we call the Big Bang. And it does it in the form of, well, my first miracle of physics. I told you there are going to be two miracles in today's talk. Now, it's of course dangerous for physicists to talk about miracles, because you've probably been told that physicists aren't supposed to believe in miracles. Or at least if they do, they're not supposed to consider it part of the physics that they do. The notion of a miracle that I have here is not something that's really supernatural, but rather something which is natural within the laws of physics. But my point of view is that there are some features of the laws of physics that are so novel and, in my case at least, so different from what I learned when they taught me physics in high school, and so miraculous in their consequences that I think it makes sense to call those properties of the laws of physics miracles. And inflation really does depend on two of them. And the first is the one that describes how inflation produces this repulsion. And that is, it produces it through gravitational repulsion. That is, it's actually possible, just using the laws of physics as we know them, to deduce that gravity can sometimes, not usually, but sometimes act repulsively instead of attractively. And this has really been the case since Einstein's general theory of relativity, which is the accepted theory of gravity that we use today. In Newtonian gravity, gravity was always attractive. But Einsteinian gravity, general relativity, really does offer the possibility of gravitational repulsion. So the combination of general relativity with modern particle physics suggests that at very high energies, we really do expect to find forms of matter which create a repulsive gravitational field. In detail, it's materials that have a negative pressure, but I'm not going to try to explain exactly what that means. All that's important for my talk is that there really do exist kinds of materials that particle physics predicts should exist at high energies, which literally turn gravity on its head and cause gravity to become repulsive. And that's the secret of the driving force behind this inflationary behavior. So this theory called cosmic inflation proposes that at least a patch of this repulsive gravity material existed in the early universe. And we still don't really know what energy scale inflation happened at. But at least one possibility is that it happened at the scale of these grand unified theories. It seems like a very plausible possibility, which would be this 10 to the 16 GeV. And if that is the case, then I can give you sample numbers of how this inflation would really look. And the initial patch can be unbelievably small, only 10 to the minus 28 centimeters across. And a primer here on this scientific notation, what it means to talk about 10 to the 16th. 10 to the 16 is a 1 followed by 16 zeros. The GeV unit I use here is the equivalent energy of a proton. It's almost exactly 1 GeV. And when the exponent is negative, 10 to the minus 28 means a decimal point followed by 27 zeros and then a 1. So that should allow you to translate all of the numbers mentioned here. So if one has just a patch of this repulsive gravitational material, it would drive the universe into expansion. And the expansion is exponential. And what is meant by exponential is that in a certain period of time, the volume will double in diameter. In the same period again, it will double again, and then double again, and then double again. That's the meaning of exponential. And this doubling time can be incredibly short. If we're at this grand unified theory scale, the doubling time would be only about 10 to the minus 37 seconds. Decimal point, 36 zeros. The very end, the 1. That incredibly short length of time. And every interval of that time, the whole thing just doubles in size. So it doesn't take too long to go from something incredibly small to something incredibly big if you're doubling in size every 10 to the minus 37 seconds.